biomedical ultrasound for coronavirus and diagnostic detection and prevention of anomalies. Diagnostic ultrasound is a non-invasive diagnostic technique used to image inside the body. Ultrasound probes, called transducers, produce sound waves that have frequencies above the threshold of human hearing, that is above 20 kilohertz. But most transducers in current use operate at much higher frequency in the megahertz range. The ultrasound waves are produced by a transducer, which can both emit ultrasound waves as well as detect the ultrasound echoes reflected back. In most cases, the active elements in ultrasound transducers are made of special ceramic crystal material known as piezoelectric. These materials are able to produce sound waves when an electric field is applied to them. But it can also work in the reverse, producing an electric field when a sound wave hits them. When used in an ultrasound scanner, the transducer sends out a beam of sound waves into the body. The sound waves are reflected back to the transducer by boundaries between tissue in the path of the beam. That is the boundary between fluids and soft tissue, or tissue and the bone. When these echoes hit the transducer, they generate electrical signals and are sent to the ultrasound system. Using the speed of sound and the time of each echo's return, the system calculates the distance from the transducer to the tissue boundary. These distances are then used to generate two-dimensional images of tissue and organ. The transducer pulsar subsystem provides a precise high voltage pulse necessary to excite the sensors while remaining robust enough to be controlled by the neuromorphic architecture and CPU system. The analog processing sub-module correctly processes the raw ultrasound electric signal while exposing all intermediary signals and exposing a digital output to the system user. Using codes for imaging ultrasounds are high-frequency sound waves used in this medical application for diagnosis. Their frequencies can vary from 2 to about 15 megahertz for regular imaging, where in some cases higher frequencies are used for a finer surface image. The ultrasound waves originate from the mechanical oscillations of a crystal in a transducer and excited by electrical pulses, which are also known as piezoelectric effects. These pulses of sound are emitted from the transducer and propagated through the different media being imaged. and then return to the transducer as a reflected echoes of an interface. These reflected echoes are converted back into electrical signals by the transducer and are further processed to form the final image. Ultrasound flow detection. A void in a solid material reflects some energy back to the transducer, which is detected and displayed. The sound waves, like typical waves, are reflected at the interfaces between the tissue of different acoustic impedance that is linked to the density of the medium, where the strength of the echo is proportional to the difference of the impedance. On the other hand, echoes are not produced if there is no acoustic difference, hence no impedance interface between the media. The system architecture requires a pulsar system to enable the transducer to emit a signal, a high voltage pulse, which is precisely controlled in amplitude and in time, and it needs to reach the transducer. The subsystem also requires an analog processing unit. After the acoustic wave leaves the transducer, echoes appear due to the acoustic impedance discontinuities taking place in the medium being imaged. These echoes are captured by the transducer and transformed back into a weak electrical signal, which needs to be processed. Processing includes filtering the signal around the central frequency of the transducer, then apply a low noise amplification and correcting the time-based attenuation. The image is built from the envelope of the last signal, so the envelope of the signal needs to be extracted and passed to a digital converter. As a filtering and bandpass consume most of the processing power, which is about 80% of the processing power of the digital converter. As filtering and bandpass consumes most of the processing, the module allows signals envelope detection. This enables the first compression of the data to be transmitted to the user. Ultrasound image creation as illustrated in this video presentation. The envelope of the signal would have a high frequency of 1 megahertz, since echoes are typically several periods long. The analog to digital converter is required for the digitization of such signals. This implies that an analog envelope detection has to take place within this module. In order to facilitate this processing, we have used the open source 40 megabits per second data acquisition module in conjunction with the neuromorphic architecture and an IDE compatibility for the microcontroller using C++ language, Python, as well as Linux as the main operating system. Other ultrasonic applications included in this project are ultrasonography, molecular ultrasonography, and elastography. The artificial intelligence infrared imaging smart glasses uses real-time data recording, sending you automatic email notifications on over temperature readings. Customizable temperature thresholds are relayed with instantaneous proceed weight verbal feedback to your environment. So the screencasting allows everybody to monitor those entering your premises, your house, the hospital from a safe distance, minimizing the risk of coronavirus contraction. The central point of the infrared thermographic imaging system used in my design is based on a focal plane array FPA, which are integrated image sensors with the sizes of 6400 up to 1,000,000 pixels. Each pixel itself is a microbolometer with a size of 12 by 12 up to 35 by 35 micrometer square. These 150 nanometer thick thermal receivers are heated by the thermal radiation within 10 milliseconds by around a fifth of the temperature difference between object and its own temperature. Such as high sensitivity is achieved through an extremely low heat capacity in conjunction with the insulation of the evacuated environment. The temperature of the bolometer changes its resistance in turn, which is converted into an electrical voltage signal with a fast 14-bit analog to digital converters to digitize the previously amplified and serialized video signal, such as illustrated in this video presentation. A digital signal processor calculates temperature values for each individual pixel and produces the well-known false color image in real time. The infrared camera used in these smart glasses is used to take images of the surroundings. This may be the moving objects or static objects, such as people moving in the streets. Infrared cameras work in a higher wavelength region in order to measure the temperature of the surface based on the detected radiation. The images taken in this way can be recalculated to present a temperature image of the recorded group of people or objects. A false color representation allows the various temperatures to be visualized using various colors in a clear way. This allows the user to identify warm, or cold areas very easily based on the image. In this video, I will illustrate the software algorithms and models of the intelligent infrared digital thermometer medical platform. The software engineering prototype was developed in Python and C++ languages, and the BIOS resides in the system firmware. The artificial intelligence infrared thermometer system is integrated by a sophisticated optical system, a photodetector, the signal amplifier, the signal processing and display, the radiation of the measured object, and the feedback source is adjusted according to the modulator and input to the infrared detector system. The difference between the two signals is amplified by the inverse amplifier, and the temperature of the feedback source is controlled so that the spectral radiance of the feedback source is the same as that of the object being measured. Emissivity parameters. All objects reflect, transmit, and emit energy. The emitted energy can indicate the object's temperature. So, when the infrared thermometer system measures the surface temperature, the instrument can receive all three kinds of energy caused by infrared energy reflected from other light sources. The optical system of the infrared thermometer collects energy from a circular measurement spot and focuses on the detector. The optical resolution is defined as the ratio of the distance from the infrared thermometer system to the object to the size of the measured spot. The larger the ratio, the better the resolution of the infrared thermometer, and the smaller the spot size to be measured. Infrared is an electromagnetic wave with a wavelength between the microwave and visible light. The wavelength is between 1 millimeter and 760 nanometers, which is visible light, longer than red light. So, therefore, anything above absolute zero, minus 273.15 degrees centigrade, can generate infrarays. Therefore, as the temperature rises, the radiation peak shifts to the shore. The rate of change of radiant energy with respect to temperature is larger at the short wave than at the long wave. That is, the thermometer working at the short wave has relatively high signal-to-noise ratio. That is high sensitivity and strong anti-interference. The intensity of the infrared radiation emitted by objects is mainly a function of their temperature. Infrared thermography, IRT, is a science dedicated to the acquisition and processing of thermal information from non-contact measurement devices. It is based on infrared radiation below red, a form of electromagnetic radiation with longer wavelengths than those of visible light. Any object at a temperature above absolute zero emits infrared radiation. The human eye cannot see this type of radiation.